Hello friends, in this video we will derive different equations representing Bragg's law. So Bragg's law in different form. So we have in our first class derived the Bragg's law, which is given by 2d sine theta equal to n lambda. What are the different parameters here? D is the interplanar spacing. Lambda is the wavelength of the incident ray, and theta is the glancing angle. Theta is the angle between the incident ray and the plane of the crystal. So these are the parameters here. So this Bragg's law is actually the law corresponding to the real lattice, because the interplanar spacing, the wavelength of the light lambda, all those are terms in the real lattice. Now let us construct the Bragg's law corresponding to the reciprocal lattice. So we will be modifying this equation. First let us move this n term to the LHS. 2 into d by n sine theta will be our new equation. Now if d is the interplanar spacing, then d by n means another set of planes with LSS spacing, d by n spacing. So this can also represent a set of planes with other set of h, k and l values. So let me call this term d by n as d itself. The only thing is that the new d by n represent a new set of plane into sine theta. So this is our equation. Now modifying this a little further, let me move this lambda to this side and d to the left side. 1 by dhkl equal to 2 by lambda into sine theta. Now multiplying both the sides with a 2 pi factor, 2 pi by dhkl equal to 2 into 2 pi by lambda sine theta. So this is our modified equation. Now we know 2 pi by d represents a reciprocal lattice vector, right? 2 pi by d is the distance from the origin to the first point of the reciprocal lattice. So instead of 2 pi by dhkl, I can write mod g. Modulus of a reciprocal lattice vector is 2 pi by dhkl. And the other factors, 2 into 2 pi by lambda. What is 2 pi by lambda? 2 pi by lambda is k. So 2 into k into sine theta. So this is the Bragg's law. Here k represents the wave, the magnitude of the wave vector, and mod g represent the magnitude of the reciprocal lattice vector. Now let us think about this term sine theta. Theta is actually the angle between the incident X-ray and the plane of the crystal. We know the reciprocal lattice vector G is actually perpendicular to these vectors, to these planes. So if we consider a perpendicular to these set of planes, what is the angle that the incident ray makes with the G vectors? That angle will be given by this shaded angle. Let me call this alpha. Clearly alpha equal to 90 minus theta. So let us keep this in mind. Theta is the angle between the incident X-ray and the plane of the crystal in the real lattice. So if we are constructing G vectors are actually perpendicular to the planes. So the angle between the G vector and the incident X-ray will be, incident X-ray, not incident X-ray, the direction of the incident X-ray is alpha, which is equal to 90 minus theta. Now I am going to modify this equation to be equal to mod g equal to 2 into k into, instead of sine theta, I am going to write cos 90 minus theta, because according to trigonometry, sin theta equal to cos 90 minus theta. So instead of sin theta, I substituted this term. Now we know 90 minus theta is actually alpha according to our diagram. So mod g equal to 2 into k into cos alpha. Now in order to modify this equation a little further, I am going to multiply both the sides with mod g. So multiplying left side with mod g again, I will get mod g square equal to 2 into k into mod g into cos alpha. So if we look at the right hand side, we have the magnitude of k vector into magnitude of g vector multiplied by cos alpha, where alpha is the angle between the incident ray, direction of the incident ray, and the g vector, the direction of the g vector. So we know the wave vector k has the direction of the incident ray. So actually alpha is the angle between k bar and g bar. So we have here cos alpha. So this represents k bar dot g bar. What is k bar dot g bar? It is mod k into mod g into cos angle between them, cos alpha. So I can modify this to be equal to mod g square equal to 2 into k bar dot g bar. So this is another representation of Bragg's law. 2 into k bar dot g bar equal to mod g square. In the reciprocal lattice, just like we define 2d sin theta equal to n lambda, we can state Bragg's law as this equation, 2 into k bar dot g bar equal to mod g square. Now this equation can also be modified to represent 2 into k bar dot g bar plus g square equal to 0. Because in our case, g bar is the reciprocal lattice vector and so is minus g bar. If g bar is a reciprocal lattice vector, minus g bar is also a reciprocal lattice vector. So you can choose, instead of g bar, you can choose a minus g bar as well. And if this term gets a minus sign, you can move it to the right hand side. And this equation is equivalent to 2 into k bar dot g bar plus g square equal to 0. Because in the reciprocal lattice, both g bar and minus g bar correspond to the reciprocal lattice vectors. And this equation in the reciprocal lattice, this Bragg's law in the reciprocal lattice, can also be represented as delta k equal to g. This is another form of representing Bragg's law. So in effect, we have learned 3 representations of Bragg's law. First is the representation in the real lattice, which is given by 2d sin theta equal to n lambda. Then we modified this equation to get 2 into k bar dot g bar plus mod g square or simply g square equal to 0. And third, delta k equal to g. So these 3 equations correspond to the satisfaction of Bragg's condition, the condition for constructive interference, and all these 3 equations are Bragg's law. So let me explain the third equation a little more in order to get a clear picture. Delta k equal to g. What is delta k actually? Delta k is defined as k minus k dash, vector k minus vector k dash. Suppose we have a crystal lattice here. A ray is incident on this and it is getting scattered in other direction. The direction of the incident ray is called k bar, is defined by the vector k bar, and the k dash correspond to the scattered wave. So delta k is k minus k dash. And if you find this difference between these vectors, and suppose if that is equal to a g vector, then Bragg's condition is satisfied. So how do you construct the difference between these vectors? If you have two vectors, you have the triangle law. Suppose this is the incident k bar, and the ray is getting scattered in k dash direction. You can reconstruct this vector. You can actually move one of the vectors in one direction. So k bar is in this direction, and I am going to move this vector to a little upward direction to this side. So this is effectively k dash. I haven't changed the magnitude and direction. I have just moved that vector k bar and k dash. So the vector connecting these 2 points, connecting the endpoints. This vector will correspond to delta k, because that is the difference between k bar and k dash according to the triangle law. And if this delta k happens to be equal to g bar, then Bragg's condition is satisfied and you will get a bright diffraction pattern. So in this video, we learned about 3 different forms of representing Bragg's law. I hope you understood this class. Thank you.